Welcome. In this video we're going to talk about average atomic mass and isotopic abundance. Whew, that's a mouthful. And how this relates to our world, how we use it, and how it is related to what we already know about the concept of an atom. So I guess the first question to ask is, what is an isotope? Maybe when you think about isotopes you think about radioactivity. Maybe you think about Peter Parker getting that little bite from that radioactive spider and turning into the person that we know and love. And maybe you think of things like isotopes, like carbon-14. So maybe you could pause the video and ask yourself, what is carbon-14? Do I know what an isotope is, and how does it relate to the structure of an atom? So an isotope basically is when you have different flavors of the same element. And the same element mean that they have the same number of protons, the same atomic number. However, you can find different varieties where the mass number has changed. In other words, they have more, these elements have more neutrons in their core, in their nucleus. And so a good example here would be three flavors of hydrogen. One that we're familiar with, which is sometimes called protium, and then ones which are also used in certain instances called deuterium and tritium. And you can see that they have extra neutrons in their core. Now, sometimes isotopes are stable, sometimes they are not stable, and that is largely down to forces within the nucleus and whether the nucleus can stay together. So some examples of isotopes which are stable and that do not decay. A good example would be oxygen. Oxygen 16, 17, 18. Again, we're very familiar with oxygen 16. It's got 8 protons, 8 neutrons, making up the total atomic mass number of 16. But there's also some oxygens in our world which have 9 and 10 neutrons. Now you can see that not a lot, not a big percentage, so 99.76%, which is the abundance of oxygen 16, that's quite a lot, right? So almost all the oxygen is that flavor. And so if you want to look at it like Fluffy and Captain Sprinkles, then, go ahead and do that. There are also things which are called unstable radioactive isotopes. And these are things which we are very familiar with. They can help us to age things. They have lots and lots of applications. So an example that we might be familiar with is uranium to thorium to proactinium, which is a radioactive decay which we can speed up, which we do speed up in the nuclear fission process, and so on. So we begin with that uranium, and then there's a little bit of decay. So that uranium decays, spits out a helium alpha particle and becomes thorium. And this is what's called a nuclear reaction. And so an important thing to note here is that this isotope of uranium was unstable, is not going to remain as that, and is going to turn into a different element. There's a different one, which the second part of this is the beta decay of thorium, and thorium is in itself going to decay down to proactinium. So this happens in the real world. Sometimes we can kick this along with nuclear reactors and so on. Another cool thing, well, I think it's cool anyway, is to know that the average banana contains 450 milligrams of potassium. And a little bit of that potassium is an isotope that undergoes beta decay, and it creates positrons. So it creates antimatter. So there's antimatter in bananas. There you go. The second thing that I want to touch on is this concept of average atomic mass. Now maybe before, when you looked at a periodic table, you looked at it and you saw a lot of decimal places in the atomic mass number and thought, why are they there? Well, the reason is we've got to account for the fact that if we look at carbon, most of it is carbon-12, but not all of it. And some of it is carbon-13, some of it is carbon-14. And so 1.11% is carbon-13. So we really should account for that. And carbon should not have a perfect atomic mass of 12, rather a decimal place. And that's an average that we call the average atomic mass. It's the average of the masses of the elements isotopes. And so if we look at a good example of that, and the periodic table, by the way, carbon you'll see with an average atomic mass of 12.01. using these things called average atomic mass units instead of grams because it's so small, each atom. So the isotopic abundance is the relative amount in which isotope is present. So that's your percentage, if you like. Sometimes it's shown on charts like this. This is a mass spectrum of silicon. And we can see that when analyzed, most of silicon is silicon 28. But there's silicon 29 is almost 5%, and so on. So how do we calculate the average atomic mass? Well, it's determined by using the abundance and mass of each isotope. So what you're going to do is you're going to change this abundance to a decimal place, and you're going to simply say 0.99 multiplied by 39.962 plus 0.00337 multiplied by 35.967 plus, and then this written as a decimal, multiplied by 37.962. So if we look at it on screen here, we just simply change into a decimal, change the first one 99% into 0.99. We multiply by the average, by the atomic mass, and then we do that for the 3 scenarios, and we end up with a figure here of 39.948. And this should make sense because it's somewhat close to AR40. So for argon is very, very close. Most of them have an atomic mass of 40. So the overall average atomic mass should be close to 40. And if you look it up in a periodic table, it will be 39.948. And so any time that we do that, we follow that same formula. It's the percentage abundance times the weight plus the percentage abundance times the weight, and that percentage abundance is actually written as a fraction, or sorry, as a decimal, and we get its overall average atomic mass. So you could practice some sample calculations here. Maybe take a little bit of time. There's 2 main isotopes of chlorine on the board here. If you want to just pause the video and take a moment to figure out what the average atomic mass is for chlorine, and then you can check it with the periodic table. This is the wonderful chlorine on the left here, very, very poisonous. We could also look at boron. Boron has 2 isotopes, and if you could be given a question like, if the average atomic mass of boron is this, calculate the percentage abundance. So in this case, you'd have to actually work your way back following the same ratio, where you're not getting the average atomic mass, rather you're getting the percent abundance. Another example would be the isotopic abundance for K. We're going to practice these, of course, but for potassium, and remember this formula down the end, average atomic mass is X times weight 1, and then one way you could do it is to look at this decimal here as being 1 minus X times weight 2, and then you could solve for the unknowns. And so potassium has an average atomic mass of 39.1. Here's the relative or the actual atomic masses, but we don't know the isotopic abundance. So have a go at that. We'll practice it in class, and we'll fine-tune our learning.